Hello, and welcome to Controllers Tech. Before I start this video, I would like to apologize for the video quality. Actually, I lost my originally recorded file, and now I only have this 720p extracted version of it. It is still watchable, and anyway I will add the commentary at each step, so it shouldn't be a big trouble. Let's continue with the video now. We have already talked about the CAN protocol, and we have seen some examples of how it actually works. If you haven't seen those videos yet, I would advise you to watch those videos first. The link to the playlist is in the description. Today in the video, we will talk about the FDCAN, or Flexible Data Rate CAN. As the name suggests, it's an upgrade over the regular version of the CAN protocol. I am not going to talk about what FDCAN is, or how it is different from the simple CAN, or what's the use of it. I am sure there are plenty of videos on this topic. Rather, this video is more focused on the STM32 part, about the configuration, and how to start programming it. This video will cover the LoopBack mode, as there is a lot to explain in the configuration section also. Later we will move to the normal mode, where we will communicate between two devices using the FDCAN. Alright, let's see the document provided by ST for the FDCAN. It is AN5348. This here is the CAN FD format. By the way, the major advantage of using the FDCAN is, we can send up to 64 bytes of data instead of 8 bytes in the normal CAN. Also, we can transfer relatively smaller data at a higher rate compared to the normal. Here you can see the difference in the data frame between the CAN 2.0 and the FDCAN. Things are almost similar, with a little bit of addition in the control field. You can read this document to understand those additions. One additional, and important thing we have in FDCAN is the RAM. Basically all the messages, filters, and some other memory things are all stored in the RAM. So if your controller has more than one FDCAN instance, you have to share the RAM between them, and to do that you need to define the regions for both instances. But in today's tutorial we are only working with the LoopBack mode, and therefore we will be using only one instance. So we don't need to worry about the RAM for now, but we will see this in some other tutorial, where we will actually look at how to partition the RAM for different instances. Next comes the filters. The FDCAN have 4 different types of filters. During configuring the filters, we come across the 2 very important parameters, the folder ID1, and the filter ID2. All the different types of filters consider these parameters in their own ways. The range filter will filter all the messages from the identifiers, which are in the range provided by the ID1 and ID2. The dual ID filter will filter only the messages from the 2 identifiers, that is, ID1 or ID2. Leave the third one for now, we will talk about it later. The fourth is the mask filter, which is similar to what we used in the CAN protocol, and ID1 will act as the ID, and ID2 will act as the mask. Also note that I used the term filter the data rather than accept the data. This is because whether the filter messages should be accepted or rejected, can be controlled in the software. After filters, we have the reception section. We can receive data in the RX 500, or 501, just like we could in the CAN 2.0. Also, each RX 50 can store up to 64 elements, and each element can store up to 64 bytes of data. Additionally, we have the dedicated RX buffers also. There are up to 64 RX buffers available, and each buffer can again store up to 64 bytes of data. Then we have the TX buffers and TX50 to send the data. There is a lot here, and if you want further information, you can read this document. There are different test modes available for the FDCAN, but we will be focusing on the external LoopBack mode. In this mode, the RX pin is connected to the TX pin internally, but the data is still available on the TX pin, so if you want to see the output in the oscilloscope, this is what you should go for. On the other hand, in the internal loopback mode, the TX pin is disconnected from the FDCAN, so to keep the external system unaffected, while you test this particular device. In both the modes, the RX pin is disconnected from FDCAN. I am going to use the external loopback mode in this video, but you can also use the internal loopback. So let's start with the Cube IDE, and we'll create a new project. Today I will be using the H745 controller, as this is the one which has the FDCAN. Give some name to the project, and click Finish. In the meantime, let's take a look at the schematics. Here is the FDCAN. And you can see the pins PH13 and PH14 are the TX and RX pins. They're connected to the transceiver, which is already there on the board. The MCP2562FD is the transceiver used on the board I have, and therefore I don't need to connect the external module to it. If you don't have it, you need to connect it externally, just like we did it in the normal CAN module. And we have a terminating resistance, along with the jumper. And finally here are the output pins on the board, where pin 1 is connected to CAN high, and pin 2 is connected to CAN low. Alright, let's clear the pin out first. Now we will enable the clock, and I am going to use the internal clock today. I generally don't use it, but you will see in a while why I'm insisting on using the internal clock. I am leaving everything as it is, with the input clock of 64 MHz. In the connectivity section, we will enable the FDCAN1 for the Cortex-M7. Before we configure this, let's make sure the pins are correct. Here PB9 is selected as the TX pin by default, and PH14 as the RX pin. But according to the schematic, the TX pin must be PH13. So I am going to change the TX pin to PH13. Alright, we have the PH13 as the TX pin, and PH14 as the RX pin. Now we have the configuration part, and if you notice, this does not look like what we did in regular CAN. There are a lot of additional things, but we will take a look at them all. First, let's see the frame format. The CAN FD is backward compatible with the regular CAN, and if you wanted to use it as the regular CAN, you select the classic mode here. We're going to use the FD mode without bitrate switching. Let me explain this bitrate switching. Basically it allows you to have different bit rates for the arbitration phase and the data phase. So the arbitration field will be transmitted at the standard bitrate throughout the CAN bus, but different devices can transmit data at different speeds depending on the requirement. I will keep the arbitration and data at the same bitrate, so I am choosing the one without the bitrate switching. Now comes the mode. We are using the external loopback. Enable the auto transmission, and disable the other two. Alright, now comes all these weird sets of parameters. We need to use some calculator for this, and therefore here is a website for the same. I will put the link to all these documents in the description. So here you can choose, like we're configuring the FDCAN. We have the three inputs here. First one is the clock frequency, and this is the clock at which the CAN peripheral is running. Then the clock tolerance, and this is the tolerance of the actual input clock in parts per million. And the third is the node delay, which is the sum of input and output delay of the device. You can find it in the datasheet of the transceiver you're using. The board I am using has this particular transceiver in it. This is mentioned in the schematic of the board. Alright, let's start with the first one. You can find this in the clock configuration, and as you can see here, the input clock to FDCAN is 50 MHz. This frequency needs to be in kilohertz, so 50,000. Next comes the clock tolerance. This is the tolerance of the input clock, and as you can see in the clock configuration, I am using the high-speed internal clock of 64 MHz. The reason behind using the internal clock was that the characteristics are available in the device datasheet itself. In the datasheet, look for the HSI oscillator characteristics. Here you can see the HSI frequency, along with the minimum and maximum values. To calculate the clock tolerance, we have to subtract either of them with the typical value, and then divide the answer from the typical value. I am taking the max value, minus the typical value, and then divide by the typical value. Now multiply the answer with 100. This gives us the percentage tolerance. But to change it to the parts per million, we need to multiply this with 10,000. So we got 4687.5 ppm. The last parameter here is the node delay. You can find it from the transceiver datasheet. You have to look for the AC characteristics. Here you can see the propagation delay, which ranges from 90 to 180 nanoseconds, depending on whether you are using the load resistance or not. I will take the maximum delay, that is 180 nanoseconds. Now add the CAN device. Next we need to add the nominal bitrate, which is the arbitration bitrate, and the data bitrate. As I mentioned earlier, I am going to use the same bitrate for both. Here I am setting it to 500 megabits per second for both of them. Now click Recalculate. We have got ourselves the values that we can use in the parameters in CubeMX. Let's try to input them. First we have the nominal sync jump width, which is SJW under the nominal section, and the value is 13. Next we have the data prescaler, which is 1. One more thing we need to take care of, is what are the ranges of these values. Like the prescaler can range from 1 to 32, the sync jump width can range from 1 to 16 etc. If we look at the data T segment, or sync jump values, they are out of the range. So we can't just input these values like this, we need to change them. We will change this sample point in the data field, to change the data values. You can see the values are reducing. Alright, we got the option to increase the prescaler. Now the values seem to be in the range. Since we modified only the data bit calculations, the nominal part is not affected by this, and only the data values got changed. Anyway, let's input our new values in the parameters. The prescaler is 2, the sync jump width is 13, and the time segment 1 is 36. Oh, we can't have this value higher than 32. Let's keep increasing the sample point then. I changed the sample point to 75, and the prescaler is now 25, and other values looks really small too. So the prescaler is 25, the sync jump width is 1, the time segment 1 is 2, and segment 2 is 1. Alright, we are finally done with that part. Next comes the message RAM offset. As I explained earlier, we divide the RAM between the different instances of the FDCAN, but since we are only using one instance, let's keep this to 0, that is to the beginning of the message RAM. Next is the number of the standard filters and extended filters. Since we are only going to use a single standard ID for transferring the data, a single filter is enough for our application. So one standard filter, and 0 extended filters. Next is the RX500 element number, basically how many elements are we using for the RX500. I have explained this in the beginning. We are provided with up to 64 elements, where each element can store up to 64 bytes. I am going to use only one element, and the size of this element will be 12 bytes. I am choosing 12 bytes because, just to show you that we can transfer more than 8 bytes at once, which was the limitation in the regular CAN framework. We are not using the FIFO one, or RX buffers, or TX events, or TX buffers, so keep them to 0. We will use the TX FIFO elements, as we need to send the data to TX FIFO, in order to transfer it via the CAN bus. So I am using one TX FIFO element, whose size is going to be the same, 12 bytes. Next is the configuration for nominal bitrate. The prescaler is 1. And the time segments are 86 and 13. You can see the baud rate is 500 megabits, the same we set while calculating these parameters. Now since we are using the RX FIFO to receive the data, we will also use the interrupt. So go to the NVIC tab, and enable the FDCAN 1 interrupt 0. 0 is for FIFO 0, remember there are two FIFO, FIFO 0 and FIFO 1, and since we are using FIFO 0, we need to enable the interrupt 0. This completes the configuration. Click Save to generate the project. Let me close the main file for the M4 core, and build the M7 project once. I am not using the M4 core, so I am disabling all the connections to the same. This is specific to my controller, and you don't need to do any of this. Alright, we will start with filter configuration first. After the FDCAN has been initialized, we will set up the filters. First of all, we will define a filter type def for the configuration. Here is the filter configuration I am using. Alright, let's see this in detail. First we have the ID type, which is set to standard ID. This parameter sets the type of filter we are using, whether it's for standard ID or the extended ID. Next is the filter index, basically the number of the filter we are using. Since I am only using a single filter, this is set to 0. Next is the filter type. I have explained this in the beginning that there are many types of filters available in the FDCAN, and here we will be using the mask filter. Here you can see the other types of filters available, such as the range filter, which filters the data between the ID1 and ID2. We have the dual filter, which only filters the ID1 and ID2. We have the mask filter, which we have already covered in the CAN protocol. You can see the top right corner for the details. The last one is again the range filter, but without the extended ID mask. Here we are using the mask filter, with the ID as 11 hexa, and the same mask bits. Next parameter is the filter configuration. This is an important one, as it configures what should be done if the filter matches the incoming data. The options available are, filter to RX FIFO 0, or FIFO 1, or reject the data, etc. Basically, when the incoming data goes through the filters, and if it successfully passes, what should we do with that data? We can send the data to FIFO, or we can reject that data, or we can set the data as high priority. We can also send the data to RX buffers, but in this case, the filter types will be ignored, and all the data passes to the RX buffers. So we can design acceptance filters, or rejection filters, or even some high priority filters to treat some data as high priority data. We can design multiple filters, and that's why we have the filter index, which stores a particular configuration in a particular filter element. I have set the filter to RX500, so if the data is passed through the filter, it will be then saved to the RX500. Finally, we will call the function HalFDCANFilterConfig to set the configuration of the filter. I am going to use the code similar to what we did in the CAN peripheral, so here is the main file from the normal mode of the CAN video we did. First we will define the TX and RX headers, along with the TX and RX buffers. Since we are using the FDCAN, we need to change these typedef. Also the TX and RX data will be 12 bytes in this case. Next we have the message pending callback, that we will see later. In the main function, we need to start the CAN first. And then activate the notification for the new data, so the interrupt will be triggered whenever a new data is received. This will eventually call the callback function, and here we can process the data. We will do the same in our main file. Start the FDCAN1, and then activate the notification for the new data. Of course the functions are a little bit different from the regular CAN. Here the interrupt flag we are using is RX500 new message, which triggers the interrupt when a new message arrives in the RX500. By the way, the third parameter here is the buffer index, which is used if you are using RX buffers to store data instead of FIFO, so we will keep it 0. Next we have to configure the TX header, which will be transmitted along the data. Here are all the parameters we need to configure. I have already set them up, so let's see them. First is the identifier, basically the ID of the transmitter, which is set to 11 hexa. This is because we have configured the filter for this ID. Next we have the ID type, which is set to standard ID. As I mentioned before, we will not be using extended IDs. Next is the frame type, which is set to data frame. Basically it configures whether we are sending a data frame, or a remote frame. Next is the data length, which is set to 12 bytes. There is this error state indicator, which is activated. The ESI bit is the part of the arbitration field, and indicates if there is some error during the transmission. The bitrate switch is set to off, as we are not using it. Next is the FD format, which indicates what type of the CAN we are using. The FDCAN is backward compatible with the regular CAN, so if you are using classical CAN, or the FDCAN, you need to set it accordingly. We are not using any TX events or the message markers, so they are disabled. One more thing, these parameters just indicate the settings we have already configured, and changing them does not change the configuration. Basically TX headers just carry the information about our peripheral onto the CAN bus. Now that we have set up the TX header, it's time to send the data. So I am defining a variable index. And in the while loop, I am going to store its incremented value in the TX buffer. TX buffer is 12 bytes, so each time this loop runs, the TX buffer should have a new set of values. Now we will use the function, addMessage to TX FIFO queue. As the name suggests, it will add the TX buffer to TX FIFO queue, and then the data in the queue will be transmitted to the CAN bus. The parameters are the instance, the TX header, and the TX data itself. Let's run this loop every second. This completes the transmission part. Now we will see the reception part. When the incoming message successfully gets passed through the filter, a FIFO 0 callback will trigger. Here we will check if the interrupt was triggered by the new message flag. Remember that we activated the notification for this flag, such that if a new data arrives in the RX500, the interrupt will trigger. Here we will use the getRxMessage function to copy the message from FIFO to our RX buffer array. The parameters of this function are the FDCAN instance, the RX location, which is basically the RX500 in our case, the pointer to the RX header, where the RX header will be stored, and finally the pointer to the RX data, where the actual data will be stored. After receiving the data from the RX FIFO, we will activate the notification again. This needs to be done, because the HAL was deactivating the interrupt for me. If it works alright for you, then you don't need to do it again. Alright, that finishes up everything. Let's build and debug the code. I have added the TX and RX buffers in the live expressions. Let's set a breakpoint here, before copying the RX message. So we hit the breakpoint, and you can see the TX buffer has been populated with the values of the index variable. Now this function will copy the data from the FIFO to the RX buffer, so let's step over it. You can see we got the data into the RX buffer. Let's run it again, and now the TX buffer has a new set of data, and if we step over this function, the same data gets copied into the RX buffer also. So the TX buffer is transmitting some data, and through the LoopBack, the same data is received by the RX buffer. I can't show you the output in the logic analyzer, as mine doesn't have the FDCAN decoder in it. I hope this was clear. Video was too long, but this needed to be covered. I will continue this, and in the next FDCAN video I will cover the normal mode. Hopefully we will also see the RAM management. The link to the code is in the description below. Leave comments in case of any doubt. Keep watching, and have a nice day ahead.